This video is going to be talking about many of the use cases and architectural concerns that you often need to solve for while growing and supporting a large client-side application. In a previous video, we talked about 3 phases of application development, and how at each phase there is often some decline in the rate of development progress, a large reason for which is the need to refactor the application's architecture to build in support for features that it needs as the application grows. We also talked about how one of the best ways you can reduce the lost development time is by starting with a mature architecture, which Lore provides as part of the framework, along with built-in support for many common features and use cases that client-side applications often need to incorporate as they grow. In this video, we're going to be diving into many of those common functional and visual challenges that you'll often need to face, and discussing what they are and how Lore can help address them. But before we dive into any of the topics, there's a couple quick points of housekeeping that I need to mention. The first is that not all of these features and use cases we're going to talk about are covered by Lore at the time of this recording, but they do accurately reflect the roadmap for Lore. Where the concern is not currently addressed, it will be called out as being in a proposal phase, and an explanation of how Lore plans to implement it will be provided. The second point is a quick call out to InVision to give them credit for some of the screenshots I'll be using later. InVision is a user interface user experience prototyping tool, and if you haven't checked it out, I definitely recommend it. It is a fantastic tool from a really great company. When you create an account with InVision, they automatically set you up with a series of example prototypes to help you get familiar with the application. The screenshots you'll be seeing later on are going to be from the prototype in the middle, which is for a mock-up experience called Simply Social. And with that said, let's get started. And where we're going to start is actually with something that connects all of these concerns together, and that is the structure that you use to represent the data in your application. So the data structure is important because React applications and components are simplest when they're data-driven. So what does that mean? Let's take a look at this component as an example. So this component takes a single post and renders it to the browser, and that post might look something like this. But the thing we have to keep in mind is that this is really only one representation that this view might take, and it represents the static, sort of not in transition representation. But in a more fleshed out application, we might need a different component to show that the post is being loaded, or we might need to render a faded post to show that it's being updated. Or if a post had an error when we attempted to update it, we might want to visualize that somehow to let the user know that something went wrong. And so all of these are different ways to render a post. And so to truly make our component data-driven, it's important that the data it receives is descriptive enough in order for it to know how to render that resource properly. In other words, we not only need the data attributes for that resource, but we also need the context surrounding it. To help with this problem, every model that Lore provides to a component has a data structure around it that looks like this. And this structure was specifically designed to enable data-driven behavior for key use cases, and it currently has 5 fields. The ID field is the unique ID for the resource and is set by the API server after resource creation. This field is required for CRUD operations like updating and deleting resources, and is frequently used to fetch a resource based on information in the route's URL. The CID field stands for Client ID and is a unique client-side ID created by the framework itself. It is unique within the lifecycle of the application in the browser. This field is especially helpful for use cases like optimistic updates, as well as enabling blocking experiences, such as those you might see in a multi-part creation wizard. Experiences where you need to wait for server confirmation that a resource was created before moving to the next step. The state field is a descriptive label that declares what's happening to the data at any point in time. This not only includes verbs like creating and updating, but also error conditions when the server requests fail, and this field is especially useful when components need to change what they render based on the activity in the application. Basically, the use case we just talked about for data-driven components. The data field contains all attributes that describe that resource and will often mirror the data retrieved from the API server. And finally, the error field contains any information provided by the server when a request fails and returns a 400 or 500 level status code. So that covers the model data structure. Let's change our component to request a collection instead of a model and look at that data structure. So collections follow a similar pattern, though they have fewer fields, currently being state, data, and error. Just like model, the state field is a descriptive label that declares what's happening to the data at any point in time, though for collections, this will typically only communicate whether or not that collection is currently being fetched. The data field will be an array containing the models within that collection, and those models will be wrapped in the model data structure we just talked about. And finally, we have the error field again, which will also contain any information provided by the server when a request fails and returns a 400 or 500 level status code. So reviewing what we just covered, the data structure you select is important because data-driven components make for simpler React applications. The core challenge is providing context to the data that components receive, and the approach that Lore takes is wrapping data in a declarative data structure. All right, so now that the data structure is covered, let's jump into our first functional challenge, which is the AJAX abstraction tier you use to communicate with your API server. And this topic is about simplifying your API server calls. So the majority of code in React Redux applications goes into action creators, reducers, and components. And this section is about the action creators. One of the main responsibilities for action creators is making AJAX calls to the API server, listening for the response, and then dispatching actions that the reducers can pick up so that the application will update. So if you want to reduce the amount of code in your action creators, a good place to start is by looking into simplifying your server calls. In a previous video, we talked about how, with respect to Lore, if you want to interact with an endpoint, you simply need to create an empty model, and the framework will automatically supply a set of actions and reducers that support standard CRUD operations. And the way that the framework does this is by layering abstraction tiers on top of each other, each with a progressively higher level responsibility. At the very bottom, we have the XML HTTP request object, which is the API that browsers use to make AJAX calls. On top of that, we build an AJAX abstraction tier to simplify and reduce the code required to make AJAX calls. Example libraries for this would be like jQuery or Axios. On top of that, we build a REST API abstraction tier that's geared specifically towards taking advantage of REST API conventions and helping to address specific API concerns that you are often confronted with as your application evolves. An example library part of this tier would be Backbone. With something in place to help with REST API calls, you can then focus on building your actions. In Lore's case, this tier is represented by configurable blueprints that take advantage of the naturally recurring patterns within action creators in order to reduce the amount of boilerplate code you have to write. And finally, on top of that, we apply some conventions, which gives us a way to auto-configure sensible defaults into the action creator blueprints. And putting all of this together is how Lore is able to convert an empty file into a standard set of action creators. Now granted, while that might explain the concept and give you some idea of the thought process behind Lore's blueprints, it doesn't really explain how this tier works in Lore. But building that explanation up well actually takes a bit of time. So for now, we're going to end this section here, but in a future video, we will decompose the stack to demonstrate how it's built, along with the specific problems each tier is designed to solve and which libraries Lore uses to build it from. So looking at the rundown for this section, it's important because action creators compose a large amount of your React application code. And the core challenge is identifying scalable patterns you can build on and that are easy to evolve as your application needs change without having to modify dozens of files. The approach that Lore follows is configurable action blueprints with convention-driven defaults, which means that all the common code is in a single file, which you can then override or modify as you'd like. All right, so the next functional challenge is filtering. And filtering is useful for viewing a subset of data that matches a certain criteria. And it looks like this. So here we have our example application, and we're going to click on the search bar in the top right and type in a search term. Then we'll hit enter, and the application will make a request to retrieve the posts matching our search term. We'll go through a short loading experience, and once the request is fulfilled, we will see a list of posts that contain the term we searched for. The core challenge here is really preventing action reducer explosion, meaning that while sending a query to the server is fairly straightforward, the question is whether you can do it in a way where you don't have to add additional actions and reducers for every different type of question you need to ask. So let's look at how Lore handles that. So here we have our application, and we want to render the results of a query. So let's dive into the component responsible for doing that. This component is going to render our list of posts. And at the top of this component, we're calling getState as part of the lore.connect decorator and requesting the list of posts where the author ID and title match the provided criteria. The first thing lore does is alphabetize the where clause and stringify it. And what this does is that it creates a unique key that represents this query and that will be identical every time regardless of the parameter order within the where clause. Lore then takes that query key and looks in the store's state to see if the query has already been asked. For this example, we're assuming that no component has requested this data yet, so we're starting off with an empty data store. And because of that, following the pattern for this decorator, lore will then invoke the action responsible for retrieving that data. So here's our component again, and since the data couldn't be found, it invokes an action creator to fetch the data. So next, let's dive into the action. Here's an example action creator for handling this request. It expects a single parameter, being the query we're asking, and then it instantiates a posts collection, which gives us an instance that knows how to communicate with the posts endpoint. We'll dive into actions in more detail in the upcoming video about the abstraction tiers that lore uses to build the blueprints, but for now, you just need to know that this instance understands how to communicate with REST API endpoints. From there, the action then invokes the fetch method on the collection, passing in the query we want to ask, which causes a GET request to be made to the API server. And then we dispatch an action, shown on the right, to notify our application that the request is being fetched. Note that we include the query as a property in the action that gets fired. So two things just happened. First, a request went out to the API server. And the second is that an action was dispatched to signify that the request is being fetched. So let's dive into the store next to understand what it does with that action. Recall that the way the store works is that we take the initial state in the store, and then reducers process the action, and we end up with a final state that the application is notified about. So our initial state in this case is empty since we have no data. And our action declares that a request to fetch our query has been sent out. What happens next is that the find reducer looks at the query and knows that it should associate it with the corresponding payload. Once that happens, we end up with this final state where the value for state.post.find is an object, where the key is the query, and the value is the corresponding payload. So now, when our application is notified of the change, our component will once again request all posts matching that author ID and title. But this time, the data will be in the store, so no action will be fired. Instead, the component will take the data it finds and show a loading experience to the user. So now we're going to fast forward in time to when the request we sent out comes back from the server. Taking a look at our action creator once again, here we have our API response in the top right, and when it returns, our promise will be fulfilled, and our action creator will dispatch a new action. Notice that this time, we change the state to resolved, and our data field now contains the data we received from the server. So once again, we dispatch the action and dive into our store. This time, our initial state contains the data declaring our query was being fetched. And our new action has the data we received back from the server, letting us know that our query was resolved successfully. And because the query key is the same, we know that we can replace the old data with the new data, and we get our new state. And now the application is once again notified that our state changed, and the component updates the view to reflect the data we just received from the server. So that covers how filtering works in lore at the moment. Let's talk about some known areas where it needs to improve. So the syntax right now is centered around exact matches. Whatever you pass to the where clause is sent directly to the server. This works fine for simple filtering, like querying by user, but not for more complex filtering, like text searches or finding data within a certain date range. To support that, this interface needs to be expanded to include a more complex query syntax, such as, give me all the posts with a title that starts with Bako. The second known area for improvement is what I'm calling language mapping, for lack of a better term. You see the need for this situation arising when the property names used in the client side don't directly map to the property names used by the server. And this is fairly common, especially for front-end experiences that have been around during a period where the API underwent a lot of change. So this feature would allow you to map the word you use on the client side, like name in this example, to the property the server expects to see in a query, which would be title in this case. So, to review, this is important because it's a poor experience to make users mine through large datasets, so we want to provide them a way to ask the questions they need answered. The core challenge is preventing action reducer explosion, and the approach that Lore takes is to stringify the query and use it as a key in the find reducer. Future improvements will include an advanced query syntax and the ability to map across language differences between the client and server. Next up is pagination. Pagination is useful for moving through a large set of data one page at a time. And before we start talking about this, it's important to call it that this is a proposal. At the time of this recording, this is not yet implemented in Lore, but it's part of the video because it will be. It's very high up in the roadmap, and it's an important consideration to include in this list of challenges. All right, let's take a look at our sample application to see an example of pagination in action. Here we have a page showing a list of posts. At the bottom, we have some numbers representing additional pages of data. And if we click on the number 2, our data will change to reflect the next page of data. Normally, this change will also be accompanied by a loading experience as the new page of data is fetched from the server. And the core challenge here, similar to filtering, is preventing action reducer explosion, but also being able to work alongside filtering. So both of these involve slicing data up into pieces, and you need both of them to work together and side by side. So let's take a look at an example, and to do that, let's dive into a component. So this component is requesting all the posts written by a certain author. It's also requesting a specific page of data, which we extract from the query parameters and the route's URL. Similar to filtering, we're still going to alphabetize and stringify the query, but to support pagination, Lore will likely require stringifying the entire query and not just the where clause, which is what it currently does to support filtering. And the reason for keeping them separate here and not just adding the page property to the where clause is so that the application will still function properly even if a resource has an attribute called page, and that might happen, for example, if you were creating a book-related application. And just like filtering, we'll still be using that query key to check the data in the post.find state, and then invoking the appropriate action creator if the data wasn't found. As for navigating between pages in a paginated experience, the recommended pattern is to use the URL and let the router do all the work. So here the component is rendering links to view the other pages of data, and when the user clicks on one of those links, the query parameter in the route would change to reflect that page. So here you can see that the page is now equal to 2 in the URL, and doing this would in turn cause the application to re-render, and the component would get called again, but this time the value in props.location.query would be page 2 and not page 1. And so the component would then render the second page of data. So to review, pagination is important because it's generally a poor experience to show users a large amount of data unasked. Additionally, large data sets can also negatively impact the responsiveness of the application. The core challenge here is preventing action reducer explosion while also working alongside filtering. And while this feature is still in the proposal phase for Lore, the approach it plans to follow is to stringify the entire query and not just the where clause, and use it as a key in the find reducer. Next up is WebSockets, otherwise known as real-time communication. So WebSockets are useful for updating content without needing to refresh the page to detect changes. And yes, this too is in the proposal stage, and it will be implemented after pagination and infinite scrolling are supported. To illustrate real-time communication, let's focus on this list of posts currently containing a single post by Sam. At this same time, somewhere else in the world are other people writing posts, and without doing anything or touching anything, new data shows up as it's created. And this repeats, and our page continues to show us the new content in real time. So a great question to start this off. How important is this, really? For example, if you're not building a real-time application, it's easy to write it off as unnecessary and therefore not a cause for concern or consideration. So is this really something you should care about? When people think about real-time, they often think about chat or social media apps like Twitter and Slack. Applications where you interact with other people and there's a large stream of data, and if the application doesn't automatically update, your users would find themselves refreshing the page so often that it would easily be considered a usability issue. On the opposite end, we have more static applications, apps where even if the data was real-time, changes either happen so infrequently or where the visibility of the data is limited to a single individual that even if the application was real-time, you wouldn't really see a benefit. The pain of not having real-time support is pretty minimal. But the thing is, real-time is really less of a yes-no answer and more of a spectrum. So it's not so much a question of is my app a real-time app, so much as which experiences in my app could benefit from being real-time. And one common type of application that lives in the middle, and something that can frequently benefit from real-time support, are applications that grow to the point of adding support for teams. For example, you will see this with a lot of startups. They build an application that starts off as a single user app, and small businesses pick it up because it helps them solve their problem. But then, as that business grows and they have more employees, it's no longer acceptable for them to share a single username and password, which often belongs to the administrative account, with the other employees. And so they begin to request support from multiple users. The problem is that at this point, you now have multiple people looking at the same data, and not being able to broadcast to all the users in the account when that data changes can create a frustrating user experience. The downside of not having real-time support in a team app is that it can breed distrust in the software, as people find themselves needing to refresh the page just to see if there are any changes made by their coworkers. And in many instances, I've seen people become afraid of making changes to an application without first announcing their intent and asking their coworkers to stay out of that part of the app. So the takeaway from this is that while your application may not be a multi-user experience today, it's not uncommon for startups to grow to the point where real-time can really enhance the user experience. And that's why it's included in this list of features that Lore is architecting for. So with that being said, if you're not familiar with real-time apps, they're actually more similar to REST APIs than you might think. So let's take a look at a typical REST API setup. Here we have our API server, which exists at some domain, and we make HTTP requests to specific endpoints to interact with our data, get, put, post, etc. And when we make a request to one of the endpoints, the server responds to that request and sends us data. And then we do it all over again once we need to do something else. WebSockets are very similar conceptually, at least for the purposes of this diagram. They also have a server endpoint, though it's going to run on a different port than your REST API, and instead of endpoints, you have rooms that you subscribe to, like posts and comments. The biggest difference is in execution. Instead of making a request and then waiting for the response, you subscribe to a room, and that connection stays open. Then the server calls you whenever it has data that you requested to be notified about, instead of you calling the server as you do with a REST API. It's also important to call out that the responses do look a little different as well. So once again, here's the REST API concept, and here is the WebSockets concept. The point of this is really just to highlight that conceptually, the same pieces exist in both the REST API model and the WebSockets model, they just change name and form. The core challenge with this is integrating WebSockets into the existing REST API action data flow naturally, as duplicating actions for every real-time endpoint would be tedious and error-prone. So let's take a look at how Lore is planning to implement that. For context, let's run through the existing REST API data flow real quick. So with the REST API setup, the components invoke action creators, which make requests to the API server and handle the response. Then they dispatch actions, which are picked up by the reducers in the store, and then the application updates when the state changes. By comparison, here's an example diagram to show how Lore intends to integrate support for WebSockets. The plan is to create a set of blueprints that live alongside the REST API blueprints that already exist currently. The key difference is that the data the server sends to us through WebSockets doesn't match as cleanly to the actions that we want to dispatch. So the challenge here is implementing support for WebSockets in such a way that nothing else in the application needs to change, and the existing reducers can continue to function unmodified. So given the previous diagrams and discussion, the WebSockets implementation will likely be a combination of action creator blueprints that know how to subscribe to rooms, as well as a series of user-defined mapping functions to help Lore convert the WebSocket messages into an action. Let's take a look at what that might look like. And we'll start by diving into the config folder at the root of our project structure. Like everything else in Lore, WebSockets will end up with its own config file. And since Lore is trying to make things simple, the goal for the interface is to be a switch that you turn on or off, and WebSockets will then piggyback on your existing action infrastructure. By default, WebSockets will be disabled, so to use it, you would first have to turn it on. Once you do, you'll need to provide the URL or port that the WebSocket server is running on, and then supply a function or set of functions that knows how to convert a WebSocket message to its corresponding action. And we're going to focus on that function for just a minute. So to reiterate, the purpose of this function would be to convert the WebSocket message into the corresponding action. To do that, you'll need to map the room and verb into an action type, and map the verb to a payload state, though most of the time this will simply be resolved for data coming from other users. You'll also need to extract the data from the message that we want to send to the reducer. Additionally, like everything else in Lore, this WebSocket config will also be overridable on a per model basis as well, in case you're interacting with multiple WebSocket servers or the mapping pattern changes on a per room basis. Alternatively, if you only want to subscribe to a specific piece of data and not an entire room, Lore will supply functions to subscribe and unsubscribe to data, such as when you only need to be notified during the lifecycle of a specific component. Alright, so known areas for future improvement. So I'm not going to read this, feel free to pause the video if you want to, but basically polling is a way of faking real-time support by making requests to the API server on a timer. While I believe Lore should provide support for this, as many applications can benefit from a pseudo real-time implementation, it's important to call out that polling does have limits. It's really more of a band-aid or interim solution, and not something you should or really can depend on if your application really does have a high rate of change. It gets especially tricky if you're polling at a high frequency and your API is slow to respond. Browsers have a limit to the number of concurrent AJAX requests that can be made to the same domain, and under these circumstances, your application can stop being usable as requests become queued up. And with that, let's review the rundown. WebSockets are important because they can provide an improved experience, especially for team or collaborative apps where multiple people interact with the same data. The core challenge is integrating WebSockets into the existing Action Reducer data flow naturally so that it can easily be turned on or off. While this feature is still in the proposal phase for Lore, the approach the framework plans to follow is to create a series of WebSocket blueprints and then ask for help mapping the messages to actions. Next up, we're going to talk about visual cues. And visual cues are useful for providing the user with a visual indication that some action is being performed but has not yet completed. To illustrate, let's take a look at our sample application. Here we can see a loading experience as the posts are being fetched. And now we can see that the posts have been fetched, but there weren't any to be found. So we'll create one by entering some text into the green input box and hitting the enter button to submit it. At this point, we can see that the post was created, but because it's faded out, we can tell it doesn't actually exist yet. We're just being informed that the request is being processed. And once the post is confirmed to be created by the server, it pops into full color and we can interact with it. Notice that at no point during all these activities were we ever left to wonder what was happening in the application. So why does this matter? And the answer is because applications are like conversations with the user. To illustrate, let's look at a phone conversation between Megan and Blake. So Megan calls up Blake and says, "Hi, I left a number at the office. Can you find it for me? I think it's on my desk." Now, if Blake doesn't respond, Megan is going to be really confused and won't be able to tell whether or not Blake actually heard her request or even whether they're actually connected on the phone. Now, if Blake continues not to communicate and then suddenly says, "Hey, I found the number," that would be a terrible experience. We have phone etiquette specifically because we can't see what the other person is doing. Unless they communicate it to us, we have no idea. We can't even tell if they hear us. So let's look at a better experience. Now when Megan calls up Blake, Blake says, "Sure, let me just finish what I'm working on and I'll walk right over." And when she does walk over, she says, "I don't see it, let me ask someone else." And then finally, she finds the phone number and gives it to Megan. This is a much better experience. So the takeaway here is that users only know what you tell them. Communication, both visual and written, is critical to obtaining positive user experiences. And the core challenge here is making sure that all data components receive is self-describing, that any information the component needs in order to know which view to render is provided with the data. In other words, we need to enable data-driven components. Now we touched on this in the data structure section, but as a refresher, let's take a look at this example action. Here the action represents an update to a post. And in the payload, we can see that the state is set to resolved, most likely meaning the server just completed our request to create or update this post. The string in the state field is called a payload state in Lore, and the additional possibilities are shown over on the right. States for creating, deleting, fetching, and showing various errors. To demonstrate how to use these states, we're going to jump over to a component. So here we have a component that takes a single post, and what we want to do is render a spinner if we're currently fetching the post to let the user know that we've received their request and are processing it, or to display the post once the request comes back. In both cases, we simply compare the post's state to the desired payload state and change what we render accordingly. Another possibility would be to fade an element that we were updating in order to notify the user that something was happening with it. To review, providing visual cues to users is important because applications are conversations and users only know what you show or tell them. The core challenge is supplying components with unambiguous and comprehensively descriptive data, and the approach that Lore follows is to have action creators set a state property on all payloads that are dispatched so that components can simply look at the state and know exactly what the data means and what they should do with it. Next up, we're going to talk about optimistic updates. Optimistic updates provide the application with a feeling of snappy responsiveness by assuming server calls will be successful. Let's take a look at our sample application to illustrate. We're going to create a post by typing into the green input field in the middle of the page, and then hitting the Enter key to create our post. Now, immediately the post shows up in the list, but it's faded out. At this point, there's no way the post could have actually been created that quickly. Instead, this application is using optimistic updates to immediately display the post, but it's faded out to show us that it hasn't been confirmed by the server yet. Once it is, the post will be shown in full color, and we can now interact with it. The real challenge here is making sure that we can merge the non-existent data that we assume will be created successfully with the real data once it comes back from the server, and all while preventing duplicate data from appearing in the reducers. To illustrate how Lore implements optimistic updates, let's walk through an example. So here we've got our application, and it just invoked an action creator to create a post. Here is an example action creator for handling this request. It expects a single parameter, being the attributes for the post we're creating, and then it instantiates a post model, which gives us an instance that knows how to communicate with the post's endpoint. We'll dive into actions in more detail in the upcoming video about the abstraction tiers that Lore uses to build the blueprints, but for now, you just need to know that this instance understands how to communicate with REST API endpoints. From there, the action then invokes the save method on the model, which causes a post request to be made to the API server. And then we dispatch an action, shown on the right, to notify our application that the post is being processed. And the key callouts here are the ID, being that we don't have one yet, and the CID property, which is the client-side ID that was assigned to this post by the model that was just created. So two things just happened. First, a request went out to the API server, and the second is that an action got fired representing the data we currently have available. So let's dive into the store to see what it does with it. Recall that the way the store works is that we take the initial state in the store, and then the reducers process the action, and we end up with the final state that the application is notified about. Our initial state in this example is empty since we haven't fetched or created any data. And our action declares that a request to create a post has just been sent out. What happens next is that both the ByID and ByCID reducers look at the payload and store it in their respective key. Since the ID is still undefined, the ByID state stays empty. However, since the CID exists, we can store the model by its CID, and so the payload is inserted under the C1 key by the CID reducer. At that point, our application will be notified of the state change and update, and we can show our post. But because the data doesn't really exist yet, we're going to show it faded out to let the user know we're in the process of creating their request. So here we're looking at our component, and we're comparing the post state to the payload state for creating, and then rendering our faded placeholder since the resource doesn't exist yet. So sometime later, our request comes back from the API server. Taking a look at our action creator again, here we have our API server response in the top right, and when it returns, our promise will be fulfilled. And our action creator will create and dispatch a new action. Notice that this time, it does have an ID which was assigned by the server, and we have changed the state to resolved. So once again, we dispatch the action and dive into our store. This time, our initial state contains the data declaring our query was being fetched, and our new action has the data we received back from the server, letting us know that our post was created successfully. And because the CID key is the same as the CID we already have in the store state, we know that this is the same data, and we can substitute our previous payload with the new one. Additionally, because the payload has an ID this time, we can also insert it into the state through the byId reducer. And now the application is once again notified that our state changed, and the component updates the view to reflect that the post was created on the server side. So in review, optimistic updates are important because they add a feeling of responsiveness to the application. The core challenge is properly merging the optimistic and real data together, and the approach that Lore follows is to use a client-side ID to associate the optimistic and real data. Next up, we're going to talk about error handling. And error handling is useful for informing the user when things don't go as planned and providing them with the ability to correct the error and try again. To illustrate, let's take a look at our sample application. We're going to create a post, and we're going to do it by clicking the Add Post icon in the header. This launches a creation dialog where we will enter some text for our post and then click the Add Photo button to attach an image to it. At this point, we will drag an image into the dialog, wait through the uploading experience, and then, it looks like there was a problem. So here the application has detected that the image I tried to upload was too big and has displayed an error telling me so and asking if I have a smaller image. So the core challenge here is making sure that the server errors are communicated back to components so that we can inform the user when something bad happened and give them a chance to at least copy out their data or fix and retry the request. To illustrate this, we're going to start our example in the middle of an uploading experience in the application where we've already invoked the action creator to upload the image. So diving into our component, we have something like this. And since we're currently uploading the image, our model's state is going to be creating, and we'll show the uploading experience on the right. Sometime later, our upload request comes back, and we get an error that the image was too big. And depending on the API we're interacting with, we could also get some additional information like an app-specific error code and a URL we could give to the user to find out more information about the error. So our action creator is going to take that error response and fire an action. In this case, the action will contain a state signifying that there was an error creating the image, and it will embed the error response from the server in the error field. Then, once the store updates, our app will re-render. But this time, when we retrieve the image from the store's state, it's going to look like this, and we'll see that there was an error uploading the image and what the error was. So now, when the component re-renders, we can take that information to change the experience, let the user know what happened, and give them an opportunity to fix the error. To review, error handling is important because it allows us to inform users when errors happen and give them an opportunity to correct them. The core challenge is making sure that server errors get communicated to components, and the approach that Lore follows is setting an error state in the model and embedding the server error in the error field. Next up are 404 pages. And these are used to provide the user with a clear indication that what they're looking for does not exist. Let's take a look at our sample application for an example. Here we're looking at a page with a single post at the bottom. When we click on that post, we're taken to the page with more information. Now let's say some time passes and the user who wrote this post deletes it. If we saved this URL and came back at a later point in time, we would see a loading experience as the application tries to fetch the post. But this time, because the post was deleted, we should get an experience that lets us know it could no longer be found. The challenge here is making sure that components can clearly discover when a request returns a 404, because blank pages and loaders that spin forever are both terrible user experiences. To illustrate this, we're going to start our example with a loading experience in the application where we've already invoked the action creator to fetch our post. So diving into our component, we have something like this. Since we're currently fetching the post, the model's state is going to be fetching, and we'll show the fetching experience on the right. Now, sometime later, our fetch request comes back, but we get a 404 from the server telling us the post doesn't exist. So our action creator is going to take that not found response and fire an action. And in this case, the action will contain a state signifying that the post could not be found. And once the store updates and our app re-renders, the component will see that the state changed, and instead of showing the loading experience, it can render a 404 page instead. So in review, 404 pages are important because users should know when resources can't be found, and it's a poor user experience to show blank pages or have loaders that spin forever. The core challenge is communicating to components when resources can't be found, and the approach that Lore follows is detecting 404 responses and setting the model's state to not found. All right, so that's going to wrap up this video for now. To quickly review, we talked about application data structure, Ajax abstraction tiers, filtering, pagination, WebSockets, visual cues, optimistic updates, error handling, and 404 pages. What we have not covered yet is infinite scrolling, dialogues, and wizards, but we will be covering those in future videos. Until then, take care, and thanks for watching.